Okay, well, welcome back to our class on algorithms and data structures. So for this lecture, we're going to be talking about the binary search tree implementation. We just went over the Java interlude that is helpful for some of the stuff that we're addressing here. So we'll just go ahead and press on to that lecture. Here is a listing of the textbook chapter contents. And so give some overview. We'll talk about searching, retrieving, traversing, adding an entry, removing an entry, and the efficiency of the operator, plus an implementation of the ADT dictionary based on the information that we're covering here. So recall from chapter 24 that a search tree stores data in a way that facilitates searching. In particular, we saw the binary search tree, which is both a binary tree and a search tree. The nature of a binary search tree enables us to search it by using a simple recursive algorithm. This algorithm is similar in spirit to a binary search of the array and can be just as efficient. However, the shape of the binary search tree affects the efficiency of this algorithm. Since we can create several different binary search trees from the same data, we want to pick the tree whose shape provides the most efficient search. For a database that remains stable, a binary search tree provides a relatively simple way to achieve an efficient search. Most databases, however, change to remain current. Thus, we must add nodes to and remove nodes from the binary search tree. Unfortunately, these operations change the shape of the tree, often making a search less efficient. So this chapter implements a binary search tree, and in doing so describes the algorithm for adding and removing entries. Chapter 28 looks at ways that a search tree can provide an efficient search despite additions and removal. So let's get some introduction stuff here. And so as we get started, so a binary search tree is a binary tree whose nodes contain comparable objects and are organized as follows. For each node in the tree, the data is is greater than the data in the node's left subtree. The data in a node is less than the data on the node's right subtree. Figure 26.1 shows the binary search tree that you saw in chapter 24. Recall that a comparable object belongs to a class that implements the interface comparable. We use the class method compareTo to compare such objects. The basis for this comparison varies from class to class depending on the data fields compareTo examines. So here is an interface for the binary search tree. And so in addition to the common operations of a tree as given in the interface tree interface, a binary search tree has basic database generations that search, retrieve, add, remove, and traverse its entities. We can design an interface for a binary search tree as well as for other search trees that we'll see in chapter 28. Listing 26.1 provides such an interface. Note that we do not allow null values in a search tree. Thus, methods can return null to indicate failure. To simplify our discussion, the entities in the search tree must be distinct. So this is just the second part of that listing. So we'll just, you can look that over as you would like. So let's start to explore this more, understanding the specifications. These specifications allow us to use a binary search tree in the implementation of an ADT dictionary. As you will see later in this chapter, the method return values instead of exceptions to indicate whether an operation has failed. The return value for a successful retrieve, add, or remove operation, however, might seem strange at first. For example, it appears that the retrieve operation getEntry returns the same entry it is given to find. In fact, getEntry returns an object that is in the tree and that matches the given entry according to the entries compareTo method. And so let's look at an example that adds entries and then retrieves them. So imagine a class person that has two strings as data field representing the person's name and identification number. the class implements the comparable interface and so has a compare to method. Suppose that compare to bases its comparison only on the name field. Consider the following statement that create and add to a binary search tree. Search tree interface person, my tree equals new binary search tree. Person Whitney equals new person Whitney, followed by number 111223333. Person return value equals my tree dot add Whitney. So following the add operation, return value is null since Whitney was not in the tree already. Now suppose we try to add another Whitney who has a different identification number. So person Whitney 2 equals new person Whitney 444556666, return value my tree dot add Whitney 2. Since Whitney and Whitney 2 have the same names, they are equal. That is, the expression Whitney compared to Whitney 2 is 0. Therefore, the add method will not simply add Whitney 2 to the tree. Instead, it replaces Whitney with Whitney 2 and returns Whitney, the original object in the tree, as figure 26.2 illustrates. We can think of this as a way to change the identification number of a person named Whitney. So what about duplicate entries? Notice that the add method as specified in the search tree interface ensures that duplicates are never added to the tree. In practice, this restriction can be desirable for many applications, but sometimes it is not. By making a small change to our definition of the binary search tree, we can allow duplicate entries that is multiple entries that are equal according to compare to. Figure 26.3 shows a binary search tree in which Jared occurs twice. If we are at the root of the tree and want to know whether Jared occurs again, it would help to know in which subtree we should look. Thus, if any entry E has a duplicate entry D, we arbitrarily require that D occur in the right subtree of E's node. Accordingly, we modify our definition. So let's begin the class definition with an outline here. So let's begin the definition of our class of a binary search tree. Since a binary search tree is a binary tree, we define our new class from the class binary tree that we defined in chapter 25. Thus, we begin our class as indicated in listing 26.2. Note that the call by the constructor to the protected method getRootNode, which the class inherits from binary tree, segment 25.8 of chapter 25 contains a definition of setRootNode. So in terms of searching and retrieving, let's look at the search algorithms. Segment 24.30 of chapter 24 presents the following recursive algorithm to search a binary search tree. We're showing that here in the slide. While it is convenient to express our recursive algorithm in terms of trees and subtrees, our implementation of a binary tree in the previous chapter suggests that we use root nodes instead. The root node of a tree or subtree provides a way for us to search or manipulate its descendant node. The following algorithm shown in the slide is equivalent to the one just given, but describes our actual implementation more closely. So let's look at the method getEntry to start with. So as often the case with recursive algorithms, we implement the actual search as a private method. Find entry that the public method getEntry invokes. Although the algorithm returns a Boolean value, our implementation will return the located data object. Thus, we have the following methods, and we're showing the methods here in the chart. We use the compares, compare to, and equals to compare the given entry with the existing entries in the tree. But also notice we use our use of methods from the class binary node. We assume that we have at least package access to this class. You can implement getEntry iteratively as well, with or without the use of a private method such as findEntry. So for the method contains, the method contains can simply call getEntry to serve whether a given entry is in the tree. We're showing that. In terms of adding an entry to a binary search tree is an essential operation, since that is how we build want initially. So suppose that we have a binary search tree and we want to add a new entry to it. We cannot add it just anywhere in the tree because we must retain the relationships among the nodes. That is, the tree must still be a binary search tree after the addition. Also, the method getEntry must be able to locate the new entry. For example, if we wanted to add the entry Chad to the tree in figure 26.4a, we cannot add the new node to Jared's right subtree. Since Chad comes before Jared, Chad must be in Jared's left subtree. Since Brittany is the root of the left subtree, we compare Chad with Brittany and find that Chad is larger. Thus, Chad belongs in Brittany's right subtree. Continuing, we compare Chad with Doug and find that Chad belongs in Doug's left subtree. But this subtree is empty, that is, Doug has no left child. If we make Chad the left child of Doug, we will get the binary search tree in figure 26.4b. Now getEntry will be able to locate Chad by making the same comparison we just described. That is, getEntry will compare Chad with Jared, Brittany, and Doug before locating Chad. Notice that the new node is a leaf. So in terms of a recursive implementation, the method add has an elegant recursive implementation. Consider again the example given in the previous segment. Figure 26.5 illustrates the steps in the recursive addition of Chad to the binary search tree in figure 26.4a. To add Chad to the binary search tree whose root is Jared is in figure 26.5a depicts to observe that Chad is less than Jared, add Jared to Jared's left tree, subtree whose root is Brittany, as figure 26.5b shows. To add Chad to the binary search tree whose root is Brittany, observe that Chad is greater than Brittany, add Chad to Brittany's right subtree whose root is Doug, see figure 26.5c. To add Chad to the binary search tree whose root is Doug, observe that Chad is less than Doug since Doug has no left subtree, make Chad the left child of Doug. Figure 26.5d shows a result of this addition. We can see that adding an entry to the tree rooted at Jared depends upon adding to progressively smaller subtrees. Okay, let's look at a recursive algorithm for adding a new entry. The following recursive algorithm formalizes this approach in accordance with the specification of the method add and search tree interface. Recall that we decided to have only distinct entries in the binary search tree. If we try to add an entry to the tree that matches an entry already in the tree, we replace that entry with the new entry and return the old entry. To simplify our algorithm, let's assume for the moment that the binary search tree is not empty. So here's a continuation of the algorithm. So that's available for you to look over in more detail. And so we can handle the additions to an empty binary search tree as a special case within another algorithm that involves add entry, and we're showing that here. So let's look at the public method add. The public method add not only invokes the recursive add entry, it ensures that the tree it passes to add entry is not empty. Accordingly, add deals with empty trees itself. The following implementation of add adheres to the algorithm given in segment 26.14. Note the use of the protected methods set root node and get root node that are inherited from binary tree. So let's talk about an iterative implementation. So you can implement the method add entry iteratively. We will mimic the logic of the recursive version of add entry given earlier so that you can compare the two approaches. Exercise 12 at the end of the chapter suggests another iterative algorithm in case you want to look that up. An iterative algorithm for adding a new entry, the following iterative algorithm adds a new entry to a binary search tree that is not empty. And so you can see that in the chart. Here we're looking at the iterative algorithm for adding a new entry. And so you can see that in more detail. Here's the continuation. And so here we're showing an iterative implementation of the method add entry. The Java implementation of the previous algorithm closely follows the algorithm's logic. Note the use of the protected method getRootNode that is inherited from binary tree. Here's just a continuation of that, and so you can look that over at your leisure. Okay, what about removing an entry? To remove an entry from a binary search tree, we pass a matched entry to the method remove. The desired entry is then removed from the tree and returned to the client. If no such entry exists, the method returns null and the tree remains unchanged. Removing an entry is somewhat more involved than adding an entry, as the required logic depends upon how many children belong to the node containing the entry. So there's three possibilities. The node has no children, it's a leaf. The node has one child and the node has two children. We now consider these three cases. So removing an entry whose node is a leaf. So the simplest case is removing an entry is when the node is a leaf, that it has no children. For example, suppose that node n contains the entry to be removed from the binary search tree. Figure 26.6 shows two possibilities for node n. Could be either the left child of a right or the right child of its parent node p. Since n is a leaf, we can delete it by setting the appropriate child reference in node p to null, as the figure illustrates. So for removing an entry whose node has one child, now imagine that the entry to be removed is a node n that has exactly one child c. Figure 26.7a shows the four possibilities for node n and its parent. N is either a left child or a right child of p, and c is either a left child or a right child of n. To remove the entry in n, we remove n from the tree. We do this by making c a child of p instead of n, as figure 26.7b shows. If n was a left child of p, we make c be the left child of p. Likewise, if n was a right child of p, we make c be the right child of p. Is a resulting tree a binary search tree? If n is the left child of p, for example, the entry in p is greater than all entries in p's left subtree. After we remove n, the relationship is still true, and so our tree is still a binary search tree. Analogous reasoning applies when n is the right child of p. What about removing an entry whose node has two children? The previous two cases, when n has no more than one child, are really not too difficult conceptually or in practice, but the last case is a bit involved. Again, suppose that the entry to be removed is a node n, but now n has two children. Figure 26.8 shows two possible configurations for n. If we try to remove node n, we will leave its two children without a parent. Although node p could reference one of them, it hasn't room for both. Thus, removing node n is not an option. Remember that our goal is to remove an entry from the tree. We do not actually have to remove node n to remove its entry. Let's find a node x that is easy to remove. It would have no more than one child, and replace n's entry with the entry now in x. We then can remove node x and still have the correct entries in the tree. But will the tree still be a binary search tree? Clearly, node x cannot be any cannot be just any node. It must contain an entry in the tree that legally can be node n. We know that the entries in the tree are distinct. Let's target the entry that we want to remove. Assume it is in node n. Since node n has two children, target is larger than the entry in n's left child and smaller than the entry in n's right child. Thus, target cannot be the smallest entry in the tree, nor can it be the largest. So if we imagine the tree's entries in ascending order, let's let pred be the entry that is immediately before target, and let succ be the one that is implemented after. And in order traversal of the tree would visit these entries in the ascending order, prep, target, and succ. Thus, prep is called the in-order predecessor of target, and succ is the in-order successor of target. The entry pred must occur in a node in n's left subtree, suck in the node in n's right subtree, as figure 26.9 illustrates. Moreover, pred is the largest entry in n's left subtree. Thus, pred is the entry that is immediately before target. Suppose that we are able to delete the node that contains pred and replace target with pred, as figure 26.9b shows. Now, all the remaining entries in n left subtree are less than pred is needed. All the entries in n's right subtrees are greater than target, and so are greater than pred. Thus, we still have a binary search tree. So how about let's consider locating the entry pred. The previous segment assumed that we could find targets in order predecessor pred and delete its node. So let's locate the node that contains pred. Consider again node n in figure 26.9a before target is removed from the tree. We already know that pred must be in n's left subtree, and that pred is the largest entry in that subtree. Therefore, pred occurs in the subtree's rightmost node R, as figure 26.10 illustrates. The node R cannot have a right child because if it did, the child's entry would be greater than pred. Therefore, node R has no more than one child and so can be removed from the tree easily. So let's consider an example. So figure 26.11 shows several consecutive removals from a binary search tree of names. The first algorithm given in the previous segment is used. To remove Chad from the tree in figure 26.11a, we replace it with an in-order predecessor, Brittany. We then remove the node that contains Brittany to get the tree in figure 26.11b. To remove Sean from the new tree, we replace it with inordinate predecessor Reba and remove Reba's original code. Thus, this gives us the tree in figure 26.11c. Finally, to remove Kathy from the tree, we replace it with an in-order predecessor Doug and remove Doug's original node to get the tree in figure 26.11d. So anyway, we're just moving through these figures and you can see that. So let's talk about removing an entry in the root. Removing an entry that is in the root of the tree is a special case only if it actually removes the root node. That will occur when the root has at most one child. If the root has two children, the previous segment shows that we would replace the root entry and delete a different node. If the root is a leaf, the tree has only one node. Deleting it results in an empty tree. If the child has one child, as in figure 26.12 illustrates, a child in either a right child or a left child. In either case, we simply delete the root node by making the child node C the root of the tree. Let's talk about a recursive implementation. And here's the algorithm. The entry to be removed from the tree is the one that matches the object's passed to the method remove as its argument. The method returns a removed entry. The following recursive algorithm describes the method's logic at a high level. So let's look at the public method remove. We have several details to consider before implementing the previous algorithm. The public method remove should have only one parameter and entry. So such as the method add calls that the private recursive method add entry remove will call a private recursive method remove entry. As we mentioned in segment 26.8, we will pass the root of the tree instead of the tree itself to remove entry. Since the method might remove the root node from the tree, we must be careful to always retain a reference to the tree's root. As a result, we make remove entry return a reference to the root of the revised tree, which remove can save, but remove entry must also give to remove the entry it removes. The solution is to pass another parameter, old entry, to remove entry and have the method change its value to the remove entry. Thus, the header for remove entry will be as we're showing. For the private method remove entry, since remove handles the communication with remove entry, most of the algorithm of segment 2628 is left for the remove entry. If the entry to be removed is the root, remove entry calls a yet to be written method remove from root to remove it. If the entry is in either of the root subtrees, remove entry calls itself recursively, and the implementation of remove entry is shown here. So what about the algorithm remove from root? The previous method remove entry removes the entry in the root of a given subtree by calling the method remove from root. With that method, in that method, we see whether the root node has 0, 1, or 2 children, and then proceed according to the discussion in segment 2620 through 2627. If the given node has at most 1 child, we delete the node and its entry. To remove the entry in a node having 2 children, we must find the largest entry in the node's left subtree. Remove the node containing this largest entry. The largest entry then replaces the entry to be removed. And so the following algorithm we're showing here summarizes these steps. So here we're looking at the private method remove from root. The implementation of the previous algorithm calls the private method find largest and remove largest, which we will write shortly. Although remove from root is not recursive, both find largest and remove largest are. Given the root of the subtree, remove from root returns the root of the subtree after a node is removed. Here is a private method find largest. The node with the largest entry will occur in the rightmost node of a binary search tree. Thus, as long as a node has a right child, we search the subtree rooted at the child. The following recursive method performs a search. Here is a private method remove largest. And so to remove the node with the largest entry, we cannot simply find largest. We simply call find largest and then remove the return node. We cannot remove a node from a tree knowing only its reference. We must have a reference to its parent as well. The following recursive method removes the node with the largest entry, that is of the rightmost node, but unfortunately it must repeat the search that find largest just performed. So here's an iterative implementation for us to consider. The pseudocode, recall that the method remove is given an entry that matches the entry to be removed from the tree. So remove's first step is to search the tree. We locate the node whose data matches the given entry, and we note the node's parent, if any. Whether we delete the node we found or another one depends on how many children it has. Although segment 2619 listed 3 possible cases, we can collapse them into 2 cases. The node has 2 children, and the node has at most 1 child. In the second case, we delete the node itself, but if the node has 2 children, we delete another node that has at most 1 child. That is, we transform case 1 into case 2. And so the pseudocode here describes what the remove must do. Here's the public method remove, the implementations. We will implement the major steps of the previous call algorithm as private methods that remove can call. The private method find node locates the node that contains a match for the given entry. Since we need a reference for that node as well as one to its parent, we make find node return a pair of nodes. To that end, we design a private class node pair that has constructors, and the accessor methods get first and get second. Node pair will be an inner class of our class binary search tree. The private method get node to remove finds the node containing the inner in order predecessor of the entry in a given node. Since we also need the node's parent, the method returns a pair of nodes as the instance of the class node pair. Finally, the private method return node deletes a node that has at most 1 child. We give the method references to the node and its parents, if any. Using these private methods, we can implement remove as we're showing here. Here's part 2 of that, so you can look that over. And here we have the private method find node. To find the node that contains a match for a given entry, we use the compare to method within a loop to compare the given entry with the other entries in the tree. The method returns a pair of references to the desired node and its parent as an instance of the class node pair. Thus, find node has the following form as we're showing. Here is the private method get node to remove. After remove locates the node that contains the entry to be removed from the tree, it proceeds according to the number of the node's children. If the children has 2 children, must remove one node, must remove another node that has no more than 1 child. This private method get node to remove finds this node. In particular, the method implements the first step of the pseudocode given in segment 2625. Find the first most node R in N's left subtree. Here, node N is a current node and node R is right child. The details of the step are described by the pseudocode shown in this chart. Here is the Java code to implement the get node to remove, and you can look that over. The private method remove node, our last method, assumes that the node to remove, call it node to remove, has at most 1 child. If node to remove is not the root, parent node is its parent. The method begins by setting child node to the child, if any, of node to remove. If node to remove is a leaf, child node is set to null. Then the method remove node to remove, accounting for this case when the node is the root. If we set the root of the tree to child node, realize that we will correctly set the root to null if the node to remove is a leaf. In terms of the efficiency of the operation, each of the operations add, remove, and get entry requires a search that begins at the root of the tree. When adding an entry, the search ends at a leaf at the entry is not already in the trees, otherwise the search can end sooner. When removing or retrieving an entry, the search ends at a leaf if it is unsuccessful. A successful search can end sooner. So in the worst case, these searches begin at the root and examine each node on the path that ends at a leaf. The longest path from the root to a leaf has a length that equals the height of the tree. Thus, the maximum number of a comparison that each operation requires is directly proportional to the height h of the tree. That is that the operations add, remove, and get entry are all big O notation h. Recall that several different binary search trees can contain the same data. Figure 2613 that we're showing here contains 2 such trees. Figure 2613A is the shortest binary search tree that we can form from this data. Figure 2613B is the tallest such tree. Okay, that's the end of the information for this lecture. Thank you very much.